So what we are going to discuss today is the deduction theory, right? Right. This is what the topic what we are going to discuss. This is the second part of this particular course, right? So what does it mean? So you have a transmitter and you are transmitting the samples like x1, x2 like this, xn through the channel. So this is the channel here, right? And in the receiver section, you are getting that discrete samples, right? Like this, yn. So y1 corresponds to x1, y2 corresponds to x2, and so on, right? It is like that. So this y1 corresponds to this x1 and so on, right? So basically, in this case, this x1, x2, that subscript indicate that it is a time instant. The first time instant you are transmitting, the second time instant you are transmitting, and so on. This is the nth time instant you are transmitting. But what you can actually transmit is a symbol. So for instance, if I'm using the number of symbols is just 2, it means that you are going to transmit something like 10110, like that. This is what actually you are going to transmit from the transmitter section, right? So in the receiver section again, right? So what actually you get in the receiver section, it could be the same or different, depends upon this channel characteristics, right? So it is going to be something like 1 1 1 1 and 0, let us say like this. In this case, when 1 is transmitted, you are getting 1 here, but when 0 is transmitted, you are getting this 1 here. This is the error there in this. But when you see this one, there is no error here, right? So when you transmit actually 1, it may end up with 1 or 0. Similarly, when you transmit 0, it will end up with what? 0 or 1. That is having some characteristics, So the characteristics of the channel will determine you, right? What is that probability that you get 1 when 0 is transmitted, and then probability of getting 0 when 1 is transmitted. Like it is like, you have here a 0 and 1. This is 0 and 1. We have, right, this channel characteristics here, right? So it is connected like this. So this is p of 0 given 0. This is p of 1 given 1, and you have here p of 0 given 1, and then this is going to be your p of 1 given 0. So basically this is p of y by x matrix, right? So this is the channel matrix what you are having here, right? It is like, let me write it at the bottom. The channel matrix, what you see here is p of y by x, that is equal to, you can write the channel matrix like this. So here you have this one, what is being transmitted, the random variable associated with this transmitter section, and this is the random variable associated with the receiver section. And remember that you should not get confused. Here this x1, x2, they are all the symbols. It's better that I use that symbol itself here so that you will not get confused, right? So let me use 0 and 1 here. Instead of putting x1, x2, let me put a 0 and 1 here. So but remember that this is associated with the transmitter section, this is associated with this, the receiver section. So x here and this is y here, and the elements are like probability of 0 given 0 in this, and this is probability of getting 1 when 0 is transmitted. this probability of 0 when 1 is transmitted, and here finally probability of 1 when 1 is transmitted. It is like that. As you already know, this row wise when you add, you should get 1, right? So that is very important, right? So this is a channel character, right? So now the detector, what it is going to do, whatever you actually got as a raw detection, right, immediate after channel, right? You of course you have a circuit here, right, like thresholding, right, and then you have to decide whether it is 1 or 0, and that is the reason why you are getting this, right? So you have a circuit the receiver section to detect it, right? But now what I'm talking is one more box here. It is basically this is the normal detector, right? So where applying the threshold and then getting these values and all, right? Now you are going to have one more box, which is basically the detector, right, which exploits the characteristics of the channel matrix and which improvise, let me say that it is improvise the detection, right? For instance, what does it mean is, in the input of the detector, right, if it is 1, right, it may even get a new sequence here, 1 0 1 1 0. So in this case, what is happening here is, when this 1 is transmitted, you are getting 1, fine. But when 1 is transmitted to this detector, when 1 is given to this detector, right, you see that there is some correction happening, right? So you are declaring that is a 0. Happily, that is the original here. So originally what was transmitted is 0 in this, and your detector is helping in getting back this, even though the received signal is actually 1, the detector is helping in improving that detection rate. As you see that in this case, whatever we transmitted, right, 1 0 1 1 0, the same thing only we are getting in the receiver section, but it is not 100% right. After detection you will get this detection, not necessary, right? So you can only improvise, it doesn't mean that you are going to get this 100%, right? For example, in this case, suppose that if it is 50% detection here, the raw, right? So but after applying this detector, it may end up with like 98% or 99%. That itself is the great, right? So that is what you are going to do. Now let me put that problem statement like this. You are given actually this channel matrix. That is the problem. You are given a channel matrix, right? You have to design the detector, right? That is the problem, right? So what is that you are going to do in this case? That is what we are going to discuss today, right? So let me start that. So we are going to discuss this one for the discrete case as well as this continuous case. What we discuss now is for this discrete memoryless channel. For that model only we are actually discussing. For the discrete memoryless channel, the problem statement is, you are given a channel matrix is given. You need to design the detector that improves the detection rate, right? So that is the problem, right? So now how to construct that detector? Before that, what does it mean? What is that it mean, right? So in this case, the random variable y is going to have either 0 or 1, right? As you just recall that whatever I told little earlier, right? So this is the I'm just drawing only this detector block alone, right? So here what you receive in the receiver section is going to be either 1 or 0. Here there are only two choice for it, right? And then you need to detect it, or you need to decide, right, whether it is 1 or 0, right, based on what is that input, right? So now mathematically we can say that the detector is basically the problem of finding out the partition set. We have two set here, gamma 1 and gamma naught, right? So you are going to divide, right, or the otherwise the partition whatever is available, whatever the possible outcomes, you can have it in the receiver section into two set. Basically, that should be the partition set. It means that it should end up with union, I mean that universal set here, right? 0, if I do this union of these two sets, right? So that is one thing. And there should be the disjoint, that is also important, right? So in this case, right, we are having this two set gamma 1 and gamma 2, right? How to do this partition, right? So we have 4 combinations here. This is gamma naught in this, and this is again, let me write this gamma 1 and then gamma naught, right? And we have this gamma 1 and then gamma naught, right? So we have this, like, 1 0, we can have 0 1, and then we can have 1 0, and this is null, and this is null, and this is going to be your 1 0. What does it mean? Basically, how to interpret this? We are doing this partition, fine. What does it mean? This is actually giving you the rule for the deduction. Each 1 2 3 4 individually, they are going to be the rule for you, right? So what does it mean, right? Say for instance that the first one we'll consider now. Okay, just a moment. Okay, let me take the first one. Yeah, the first one we will consider now. What does it mean? Gamma 1 is equal to 1 and gamma naught is equal to 0. What does it mean? How you interpret that? You have to look for whatever the elements available in gamma 1, right? So those are all the set, right? When you receive in the receiver section, you have to declare that is actually belonging to the transmitter section as 1 here. That is the meaning of it. It means that if I receive y equal to 1 in the receiver section, as far as this first rule is considered, you can declare that whatever is being transmitted in the receiver, transmitter section is 1 here. Similarly, when you receive y equal to 0, you can interpret that whatever is being transmitted from the transmitter is x equal to 0 here. That is the of it. Whatever is available in this gamma 1, right? So that one, is the x being transmitted from the transmitter. It is like that, right? So it is like, when you, so here, for example, in this case, the second case, I'm now writing the second case, right? So what is that? Gamma 1? Gamma 1 is 0. It means that you are going to declare that it is 1 when x is 0. So it is just a invert operation what you are doing. When you receive 0, you are going to declare that it is 1 here. So that is the meaning of it. You are doing this inversion here. So that is a rule, second rule we are using. So in case of this third part, that is the interesting part here. Irrespective of whatever, right, you receive, that means that either 1 or 0, both. Either if you receive it as a 1 or 0, your detector is going to declare that it is 1 only, whatever is being transmitted as a 1 here, right? It is like, when x equal to 1 and, right, or let me put it as or, right? So or x equal to 0, right? So either if it is x equal to 1 or x equal to 0, you are going to declare that what is, I'm sorry, it should be that y here, please. So whatever you receive here is either 1 or 0, right? You are going to declare that whatever is being transmitted from the transmitter is 1 only, x equal to 1 only. And in the last case, it is just the reverse, right? So either you receive, right, 1 or 0, right? you are going to declare whatever is being transmitted from the transmitter is going to be the 0. You may wonder, what is this? This is okay, this is coming, it follows, right? Whatever you have the input to the detector, right? So it is like, let me explain with this detector box, right? So the detector for this first rule, if I am using this as a rule for this detector, or the detector is designed in this way. Designing the detector means you have to form a rule, that's it. You have to divide, you have to form a partition. Say for example, the detector is designed with the 1. What does it mean? It means that, suppose that the input to the detector is like this, the output is also going to be like 1 0 1 0 1 0. Same thing, there is no change in it. This is for the first, right? So for the second block, I mean second case, right? So you have a detector, right, like this, and let me use the same sequence here, 1 0 1 0 1. If I am giving that as an input to this detector, what it does is it just invert it, right? So it is 0 1 0 1 0. It is like that. And the third one is, you have a detector, right? And you have this input is again 1 0 1 0 1. And this detector, irrespective of whatever you have, this 1 0 1 0 1, whatever it is, you are going to detect it is 1 1 1 1 1, like this, all the things as 1, right? And finally we have this fourth option, right? So you have this detector block, and you are going to have this 1 0 1 0 1 as an input. In that case, you are going to declare, irrespective of whatever you receive, you are going to detect as what? 0 0 0 0 0. It is like that, right? So now we have to find out the rule. That is the meaning of this detector. You have to find this partition here, this partition of whatever you receive in the receiver section. But on what basis? On what basis? And is it worth to have this third and fourth rule? So it means that the detector is always saying that it is 0, right? Will it be applicable in practice, right? All those things we can actually discuss one by one, right? But we have these 4 possibilities available, right? So that is what we are exploring, these 4 possibilities, right? But what determines that? How to fix whether it is that first rule is best, or second rule is best, or third rule or fourth rule is best to assign for the detector, right? So what we are going to do is we are going to form a objective function, right? So that is what we are going to discuss now today, right? So we have to form an objective function, and which rule is actually giving you the least, right? We have to form a cost function, right, associated with that rule, right? And we have to see which rule is actually giving you the least, right, that cost function. And that rule we are going to use it for the final design, right? So we'll have a quick recap of what we discussed now, and we'll go for that objective function, right, quickly, right? So this is what I'm telling now, what you see here, right? Consider the symbols transmitted from the transmitter be the outcomes of the random variable x, right? So it is something like 0 1 0. In this case, I have chosen this number of symbols as 2, so you are going to be like this. And the receiver section, we also consider the corresponding symbols received in the receiver be the outcomes of the random variable y. So it is something like 0 0 1 0, like that. It is going to be there. And we have a channel characteristics which is given by this probability of y given x, which we already know. And now this is very important statement, that fourth one, detection, right? The setup or designing this detector involves partitioning the observation set. This is a more general definition, because it is not necessary that y is always discrete. In this case, is y is discrete, what you see here. It could also be the continuous, right? We are going to discuss that part also, right, after finishing of this. For simplicity, we are now discussing about the discrete, but we have the continuous version of that. Whatever we receive in the receiver section, this y, would be the continuous also. In this case, we are considering that it is a discrete, right? X is discrete and Y is discrete, and hence is what we call it as discrete memoryless channel model, right? So now the idea is you have to do the partitioning, right? The observation set. For example, in this case, this observation set Y that has either what 1 or 0. These are the two symbols possible in the observation set. We are going to do this partitioning, right? So we say that we get these two partition set. One is gamma naught, the another one is gamma 1. How you interpret this set? Suppose that if the observation, that is Y, whatever you observe, right, if it lies in gamma naught, we have to interpret that what is being transmitted from the transmitter is 0. The subscript naught will indicate that. And similarly, if the observation lies in that set gamma 1, we have to interpret that what is being transmitted from the transmitter is 1, right? So it is like that. Now how to fix the rule, that is more important, right? So we go for what is called this objective function. This is the objective function you are going to have here, right? So this is the cos function, right, when 0 is transmitted. You see that I explain you, like this is actually coming from the channel matrix, right? So you are going to assign some cost, right, for doing some error in that detection, right? See, for example, when 0 is transmitted originally and you are declaring that it is 0, see, you have to understand this is not the raw channel matrix, right? Whatever I'm writing now is about the characteristics of the detector, right? Detector itself will have some characteristics, right? So what is that characteristics? It is going to have some rule. After getting this rule, still you get some error, right? So still this detector can perform what? Mistake, right? So this probability of 0, 0 is not actually associated with the raw channel matrix. It is associated with the error involved in the detector after applying the rule. So don't get confused in this case, because I'm using the same notation. The channel matrix is different now, right? So don't get confused, right? So what is given to you is, right, you are going to have the probability of declaring that it is 0, right, when 0 is transmitted. So this is what this probability associated with saying 0 as 0. There is no error in it, right? But when you say 1, right, when 0 is transmitted, we have error associated with that. So we have to assign some cost here, and that cost is what we call it as C10. In practice, ideally speaking, right, so we need not actually assign the cost for the rightly identified case, right? When 0 is transmitted and you are saying that it is 0, we need not actually have that cost in it, right? In fact, we can actually put this C00 as 0 here, right? But to make it as a more general expression, it is given like this. In practice, we can actually fix C00 as 0 here, right? So we need not assign any cost of saying 0, right, when 0 is transmitted, right? There is no penalty for it. But there is a penalty of saying 1 when 0 is transmitted, right? So you understood the point, right? When you say that as 1 when 0 is transmitted, you have a penalty for it, right? So C10, you have to give some value for it. So it is not going to be equal to 0. Some other value we are going to fix, of course, less than 1, right? And then you have here that another set of error when 1 is transmitted. This is the error when 0 is transmitted. It's a cost function, right? And we have this error when 1 is transmitted. It is like this. You see that probability of saying 0 when 1 is transmitted, right? So this is the error, and we have a cost involved in it. That is C01 is actually not equal to 0. But when it comes to here, when 1 is transmitted and you are declaring that it is 1 here, and we have a cost function here, and usually we can fix this C11 as 0 here, right? But you say that, we are having two different cost function, I mean this constant, right? C10 and C01. Why should we have two different values for C01 and C10? See, for example, let us consider the application like radar application, right? So in case of radar application, our goal is to check whether the target is present or not, right? The presence is represented with 1 and absent is represented as 0. So you have two errors actually associated with that. See, probability of 1 given 0, what does it mean? It means that originally the target is not present. You see that this is 0 indicate that target is not available. Originally target is not available, right? Target is not available, but you are declaring that the target is present, right? It is, you are saying that the target is present. It is a error only, right? You are originally the target is not available, but you are saying that it is a present, right? So you have the other way around, right? So you have 0 given 1. In this, target is actually available. You see that the target is available, but you are saying that it is not available, right? It is absent, right? So it is available, target is available, but you are saying that it is absent. This is also the error. But what do you think that it is crucial, the first one or second one? You type it on the chat window. What is more crucial in radar application? Is that both error has a equal impact? Which is critical, 1 or 2? Yeah, yes, 2. Many of you are writing that it is 2, right? So it means that what? The target is actually available and you are saying that it is absent, right? So that is what of course you intuitively you understand that even though both are error, right? So we cannot treat both the error equally. We cannot treat both error equally, right? So that is the reason we are actually assigning two different cost functions. See, this is what is this? The target is not available, and then you are saying that it is a present, and target is available and then saying that it is absent. It is what we call it as miss. You are missing it, right? And this one we say that it is a false alarm. This is a false alarm, right? This is about this probability of miss here, and this is involved that probability of false alarm, right? So in that case we understand that the second one, right, missing is more critical. False alarm is fine because if it is not there, okay, fine, right? But missing the target will actually makes you hurt, right? So that should not be, right? So that is the reason we are assigning two different cost function here, C10 and C01. But in telecommunication, if this both zeros and ones are equally important, right? So just the data, if I want to transmit, in that case I need not actually have two different values for C10 and C01. In that case I can simply fix that value as 1 itself, right? So let me put that as hereafter, right? So even though both are going to be different, depends upon that application. For simplicity now, let me choose this C01 is also 1, C10 is also 1, and then C11 is 0. It is like that, right? So now the final average cost, right? So we know that this is the cost involved when 0 is transmitted, right? And this is the cost involved when 1 is transmitted. But from the transmitter, the zeros and ones, they are not actually coming equally. They are not equiprobable, right? the number of zeros and ones, what is being transmitted from the transmitter, they are not actually equal, right? So in that case, we have to give this weightage for the number of zeros available in the transmitter and, right, being transmitted from the transmitter, right? It is like that. So P is basically the probability of zero being transmitted from the transmitter, probability that zero being transmitted from the transmitter. So it is like this. So now we can, of course, expand it after substituting this cost function value. This value is also here. B naught, this one I am going to make it as completely removed because C naught naught is 0, and this one I am going to replace with 1 here, and this one I am going to replace with 1 here, and this one fully I am going to make it as what, 0 here. So we get this CB as, in place of B naught, I am going to simply replace that one with probability of 1 given 0, right? So it is like this probability P, right, into this probability of 1 given 0 plus 1 minus P. In place of B1, we have what is left out is probability of 0 given 1. So you can write it as simply probability of 0 given 1 here, right? So this is the Bayes cost, very important cost what we are obtained. This is called the average cost, right, which we call it as a Bayes cost, right? You have to find out the rule for the detector. You have to, this is the detector, right? So you have to find out the rule for the detector such that this cost function, the Bayes cost, is getting minimized. That is the goal. That is what the thing you are going to have here, right? So this is what we are having, right? So for instance, remember that all these probabilities are rated with the detection rule associated with the detector, right? This is not the raw channel matrix. Once again, I'm emphasizing this point. Even though I am using that same notation, right, you have to be careful. We are not actually, right, this in this expression, this is not the mere channel matrix. It is a different thing. Channel matrix, right, is a different, right? It is like, you have what is being transmitted from the transmitter, and you have the channel, and then you have this receiver. This is Y here, and this is X here, and now you are actually applying the rule. Detector is doing that. Detector itself can do mistake, and that mistake is what actually we are talking about. Detector itself is going to have some error, and that error only we are talking about here. And probability of saying 1 given 0 is all associated with what the detector says, not with the error in between what X and Y. The error involved, already we have a error in it, right? So that is the channel matrix. That is the channel matrix, right? So I'm using the same notation. That is the reason I'm telling once again, you should not get confused, right? See, this probability of 1 given 0, this is what I'm talking about, the detector only. The error involved, right, by doing that, done by this detector. I mean, this is also does the mistake, right? When 1 is there, right, originally we have 1 being transmitted, and here you are giving 1, right? So if the detector says that it is 0, right, with reference to what is being transmitted, right, even though Y ends up with that correct answer, right, detector is actually doing the wrong answer. It is actually detecting 0 with reference to what is being transmitted from the transmitter. You see that? You understood the point? So this is like you are saying 0. You are saying 0, right, absence, but originally 1 is there. In radar context, it is like you are saying that the target is not there, but originally the target is there. But remember that immediate after the channel, that random variable Y also says that it is 1. Fine. This itself is saying 1, but detector is not proper in such a way that it is not favoring, right? So you have a error in it. with reference to what is being transmitted from the transmitter. This is the error. This is the error. This is the error done by the detector. I am talking about that error only. You have to be careful. I am not talking about the error involved. For example, we have one more analysis here. For example, originally 1 is transmitted and y is actually 0, right? And then your detector is able to correct it, and it is say that it is having 1. Now you see that with reference to this original, right, the target is present and detector is also saying that it is present, right? So there is no error. That is what I'm talking about. As far as the detector is considered, there is no error with reference to what is being transmitted from the transmitter, right? So what I'm trying to say here is this probability is connection between what is the output of the detector and what is originally being transmitted from the transmitter. With reference to that only we have to see this, right? So I hope this is clear. I think you will get little more clear if I go for one particular example, right? So we'll do one example, then still you will get it as more clear, right? So after that, if you have any questions, I will answer that, right? So because the example will give you the clarity, right, of what I am actually talking about, right? So now we know the rule, right? So let me write this rule. 4 rules we are having, right? So it is like gamma naught is 0, and we have this gamma 1 as 1 here, gamma naught is 1, and then gamma 1 is 0 here, and we have this gamma naught as 1 0, and then let us say that gamma 1 is going to be that null in this case, and finally you have this gamma naught as null, and then gamma 1 as 1 0. So this is given to you, and what is given to you? You are given a channel characteristics, right? So let me have a channel characteristics like this, right? So we have to right, get a value which is valid channel characteristics. That is very important. As you know, right, we know that this probability of 0 given 0 condition on the same thing, right? So if I have this probability of 1 given 0, that should be end up with 1. So given the same condition, the possible outcomes, if I do this probability summation, that will end up with 1 here, right? So with this, so this is going to be your probability of 0 given 0. Let us say that this is 0.3. I'm just arbitrarily choosing this, right? And this one is the probability of 1 given 0, so that should be 0.7 here. I mean, this is arbitrarily chosen, right? So now this probability of 0 when 1 is transmitted, let us say that it is say 0.4, and probability of 1 when 1 is transmitted, it should be 0.6 here, because you know that it should satisfy this rule, right? Probability of 0 given 0 divided by probability of 0 given, I'm sorry, probability of 1 given 0. So that should, if you add, that should end up with 1 here, and similarly this should end up with 1. Probability of 0 given 1 plus probability of 1 given 1, that should end up with 1 here. So we need not have this expression here, right? So this is the channel matrix what is given to you. Now what is that? The prior probability. We need to know about this prior probability. Let us say the prior probability of being 0 being transmitted from the transmitter is 0.3. This is again arbitrarily chosen. So all these characteristics are needed to find out what is my cost function, the Bayes cost function. If I know that Bayes cost function, then I can actually look for which rule is actually giving me the least Bayes cost function. Then I can declare that as a rule, right? So now we'll calculate this one, every rule. Say for example, that first rule. What is that first rule says? First rule says that when y is 0, right, you are going to declare that it is 0 here, right? So you need to find out what is that b, right? So let me write this expression here. cb is, right, so this probability, okay, let me put b naught, then okay, the simplified version of this cb is p into the probability of 1 given 0, right, plus 1 minus p into this probability of, right, that 0 given 1. In this you have to see that this 0 what is given here, this condition, they are all the real x, but here you have to see what are the possible values of y, right, so that the detect is at what, 1. It is like that, you are declaring that it is 1, right? You have to look for the possible values of y, right? So that actually ends up with what, detecting it as 1 here. So what I am trying to say here is, what is that y value, the corresponding y value in which you are going, the detector is going to detect it as what, 1 in this, right? It is like that. So in this case you see that the first case, so you are declaring that it is 0 here, right? So it is like that. So that is what you are saying in this case. When you have y equal to 1, you are declaring that it is 1 here, right? So now we have to think about when 0 is transmitted, when we will say that, right, when the detector will say that it is 1, the detector will say 1 when gamma 1, right? So this you have to look for this, when y is equal to 1. When y is equal to 1, you say that it is going to be what, the detector will say that it is 1. As far as the first case is considered, it is going to be that mere whatever is available in that channel matrix, that is what these characteristics we have to put it here, because the y follows the same, right? So when y is 1, you are saying that is 1, which is as usual, right? Whatever the detector detects is same as that of whatever that value of y itself, right? So when y is 1, you are actually detecting it as 1. When y equal to 0, you are actually detecting it as 0, right? So there is no change in that rule in the detector. So in that case, this probability of 1 given 0 and the probability of 0 given 1 is actually coming only from where, the original channel matrix itself. So in that case, let me write this expression 0.3 into, right, this probability of 1 given 0, which is basically 0.7 here, plus 1 minus p, that is 0.7 here, into probability of 0 when 1 is transmitted, which is 0.4 here, right? So let me go for the second rule, then you can get little more clear. We go for the second rule. Second rule, as far as this p is considered, this is going to be 0.3 only, there is no doubt in it. But when it comes to this probability of 1 given 0, right, so it is not just 1, right? So what does it mean? We have to look for what values of y you are declaring that it is 1, like that only you have to see. For what values of y you are actually declaring that it is 1 when 0 is transmitted, that is what the thing, right? So but now you know, in this case you are declaring that it is 1, right, when y is actually 0. So it means that when you get 0, then only the detector is saying that it is 1, right? So but what is being transmitted from the transmitter is 0 only, right? So that is what this is saying, right? So in that case we have to look for this probability of getting 0, because when that first block, right, is getting that 0, then only you are going to declare that it is 1. So in that case it is going to be that ulta, the probability of, right, 0 getting 0 when 0 is transmitted. So this is like 0.3 into 0.3 plus 1 minus p, which is 0.7, into, you have to look for what values of y you are going to declare it as 1 in this, right? So what is that? It is going to be, I'm sorry, I have to look for this expression. What is the probability of saying that detector is saying 0 when 1 is transmitted? You have to see that it is 1 here. So it means that when the receiver receives 1, right, so 1 given 0 in both the case, in this case 1 given 1, right, so it is like 1 given 1, which is basically this 0.6. So I have to use this 0.6 here to know about this answer, right? I will once again summarize these 4 points little later. Before that, we will go for this third case. The third case is, again, coming back to this expression, P, as far as this P is considered, we have here 0.3 as it is, fine. But when it comes to this probability of 1 given 0, so we have to look for when the detector says 1, when the detector says 1, for what values of y it says 1. In that case, it is basically the null. You never, right, the detector never says 1. That is the meaning of it. So this probability is basically becoming 0 in this case. 0 plus then 0.7 into, and when the detector says that it is 0, in both the case, right, when you receive 0 or 1, doesn't matter, right? In all the case, the detector is going to declare it as what? 0. It is, so in the receiver section, you get either 0 or 1. So in that case, your y values are going to be either 0 or 1, right? In both the case, right, you are going to declare that it is going to be that 0. So in that case, this probability is actually becoming 1. This probability is actually becoming the probability of either getting 1 or 0 when 1 is transmitted, right? That is what we are looking for. So that is actually becoming 1. So this is going to be your 0.7. Of course, this is 0, right? So the fourth one, like you have this prior probability 0.3, that is fine. And now when the detector says that it is 1, for what values of y, right, it says that it is 1. So you can see here, either you get 1 or 0. In both the case, your detector is going to say that it is 1. So in that case, this probability of 1 when 0 is transmitted, right, you have only the two possibilities, 1 or 0 in the receiver section, right? So this probability is actually becoming 1 in this case. And when it comes to the next case, you get this 0.7 into this probability of getting, declaring, the detector is declaring that it is 0 when 1 is transmitted, right? So declaring is that 0 means for what values of y you are going to declare that it is 0. So it is null here, right? So it means that this is not going to happen because you are going to get either 1 or 0 in that case. So in that case, this probability is actually becoming 0. So you are getting that final result as 0.3. Someone calculate this value for 1 and 2. Once again, I will summarize this. Before that, calculate this value. This is 0.21 plus 0.28. What is the value? Can someone write the answer here for the first and second case? Then I will clarify the doubt. It is 0.21 plus 0.28, right? So that is the case. 0.59. Okay. What about the second one? It is 0.09 plus 0.42. What is that? 0.51. Okay, fine. So now what you have to do is, among these 4 base costs, you have to look for the cost which is minimum. See that this is 0.49, this is 0.591, this is 0.7, and this is what the least among whatever the values you got. So it means that as far as this characteristics is considered, right, we have to go for the fourth rule. What is that fourth rule says? Fourth rule says this. Let me have here. You have a detector in this. This is a detector, right? So what is that fourth rule says? Whatever you get in the receiver section, right, in this at this moment, at this point, right, either it is going to be that 1 or it is going to be that 0, doesn't matter. The detector is always going to declare that it is 1 1 1, always like this. You may wonder what is the point in saying everything as 1, why it should be like this, right? You have to see the prior probability. you see that the probability of 0 is, right, let me put, the probability of 0 being transmitted from the transmitter is 0.3, but the probability of 1 being transmitted is 0.7. So what does it mean? Most of the time, what is actually being transmitted from the transmitter, right, is 1 only, because it is 70% of the time, right? And we have some characteristics in this, because it is not a perfect channel, you have error. When 0 is transmitted, it is ending up with 0 or ending up with 1. When 1 is transmitted, it is ending up with 0 or 1. We have error in it, right? So now, anyhow, we are going to have error in the transmission, right? But if the detector safely says that whatever is being transmitted from the transmitter are always 1, definitely you have a error, no doubt in it. But because you know that as 70% of the time, what is being transmitted from the transmitter is what? More, right? It is about 0.7 here. 70% of the time is being one is being transmitted, right? So you will get, right, less error comparatively, instead of doing the rule like 1 or 2 or 3, right? If you do these 3 rules, right, so the error involved is going to be the larger, but when it comes to this 4th case, the error is going to be the less, right? So this is the best among the all possible rules. That is what we are telling. It doesn't mean that it is 100% error free. No, it is not 100% error free, right? Sometimes, suppose if I know that, this is just intuitively we can understand that, suppose the transmitter is transmitting 90% of the time as 1. Every time, most of the time, right, what is being transmitted from the transmitter is 1. Only, see, out of 100, you have 90 times 1, only 10 times 0 here and there. Suppose that if I'm declaring in the receiver section all as 1, right? So hardly, right? So what does it mean? You will definitely get what? 90% of the time it is going to be the right only. So this is just looks bad as far as the statement is saying, but as far as the calculation is considered, this is actually giving you the least error, right? So this all depends upon what is the probability of the 0 being transmitted from the transmitter. If it is EQ probable, then it is a deal, right? If it is 0.5, 0.5, then it matters, right? But here we are having this probability of being 0 being transmitted, 1 being transmitted is something like a bias, right? So 1 is transmitted more, right? And we have a characteristics of the channel. Both will combine. It is not just only the prior probability, or it is not only the channel characteristics. We have both these channel characteristics and the prior probability combined together is impacting which rule I have to choose in this case, right? So I hope this is clear to you, right? So now we'll stop here. If you have any questions, we can discuss and then we'll wind up.